I'd like to talk to you about supermassive black hole studies with LSST. I'll be covering things like active galactic nuclei and quasars, as well as transient phenomena associated with supermassive black holes, like transient feeding events of them. And this is work that is not just mine, but I'll be representing the LSST AGN Science Collaboration, and I'll tell you more about that science collaboration near the end of the talk. So let me see if I can go to the next slide here. Somehow there, okay, good. So here's the outline of what I want to do today. I presume you all have heard quite a bit about the general aspects of LSST already, so I will not go into those in any significant depth, assuming you know them. I will just give a very quick review of some of the aspects most relevant to active galaxy studies. Then, after we've done that, I'll tell you about how we're going to select AGNs with LSST, as well as complementary multi-wavelength data. I'll tell you about how many active galaxies we might expect to detect and study with LSST. And then I'll go through a few specific examples of exciting science investigations one can hope to do with LSST. These include massive studies of AGN variability and transient fueling events, as well as studies of active galaxies out at very high redshifts. Those are going to be some of the highlighted topics. These are not an exhaustive list. There are plenty more exciting things one can do, but they'll give you a good idea of some of the things you can do. And then I'll tell you where you can learn more. I'll tell you about the LSST AGN Science Collaboration, as well as some future plans. So I'll just move into it now. Let's start with a very quick LSST review. So this is my single slide summarizing LSST. Just if I had to write down in one sentence, you know, what LSST will give, it will give this public optical near-infrared survey of about half of the sky in the ugrizy bands down to very great depths based on a large number of visits, 820 visits when you add things across all those filters over this 10-year period. And it's able to do this with this specialized telescope you see illustrated there on the left, which has a 6.7 meter effective diameter. It covers 10 square degrees in its field with a 3.2 gigapixel camera. And with facility like that, you can do a survey that is wide and deep and fast, as I've described over on the right-hand side of the slide. Each image will cover something like 50 times the size of the full moon on the sky. If you look at very wide field surveys in the bands that LSST covers, it will be going 10 to 100 times deeper than anything else available. And it will be fast. It will be rapidly scanning the sky with these 15-second exposures. So it provides this color movie of objects that change or move. And that's very important for active galaxies, where we know that variability is commonly seen among active galaxies. So that's my one-slide summary. Of course, this is now showing the main survey. So LSST's primary survey will be this very wide field survey covering something like 18,000 square degrees. And that's what's shown with the sort of yellowish and greenish, light greenish colors. And that survey has been optimized for homogeneity across that region. And you can see it's pretty homogeneous. It's not perfect, but pretty good, as well as having a fairly uniform number of visits and a fairly uniform spacing of those visits. In addition, there are some other selected regions that people plan to target. You can see the North Ecliptic region, the galactic plane region, and the South Celestial Pole, which will also have coverage. And again, I will presume you've learned about these things already, so I won't cover this in great detail. I do want to say a few more words, though, about these. You'll notice these reddish spots among the yellow-green color. There's 4 obvious dark red spots. These are the deep drilling fields, and they are going to be also very important for active galaxy studies. And so in addition to this main survey, which will be great for AGN studies, because it will again cover the sky every 3 to 4 days, you have these selected deep drilling fields where you will have much more intensive coverage. And that's what I'm describing here briefly on this slide. So again, about 90% of the time is going to be spent on the main survey, and the remaining 10% is going to be used for other specialized cadence programs. One of these is deep drilling fields, where LSST has already chosen a few fields that it will observe considerably more intensively than the main survey, and it's likely several additional fields will be chosen, and these have a wide variety of types. The ones that have been chosen already are well-studied extragalactic blank field survey regions. In fact, here they are in this slide. These are 4 very well-studied sky regions: Elias S1, the Chandra Deep Field South region, the XMM LSS region, and Cosmos. And these regions will each get substantially more intensive coverage than the LSST main survey. And what's being shown in this slide are those sky regions, and the LSST field is shown as the black circle, and then colored in with various boxes and other shapes are the multi-wavelength coverage in these sky regions. And so these regions have been chosen because they already have very good multi-wavelength coverage, and that's getting better all the time. And by intensively studying these sky regions, one will be able to study substantially better than normal objects that vary. And that's clearly relevant to active galaxies, as I'll tell you about in a little bit. In fact, in these deep drilling field regions, I think we will have about 100,000 active galaxies just in these deep drilling field regions. And so you'll have these large samples with extremely intensive photometric monitoring down to great depth with very high quality. Okay, so that's one example of deep drilling fields. In addition, people have ideas to do other types of deep drilling. They would like to observe a nearby cluster or a couple nearby clusters of galaxies. They'd like to observe local group galaxies, as well as specialized regions in our own galaxy. And there's also ideas to do great solar system science with the deep drilling field. So I won't cover all the deep drilling fields here, but these are going to be highly relevant, especially the blank fields to active galaxy studies. And just to give you an idea of what people are thinking about for these blank fields, instead of having the 820 visits that I've mentioned here up near the top for your typical sky region in that yellow-greenish region, for the deep drilling fields, people are aiming to get something like 5,000 to 14,000 visits per band. So this really is much more intensive coverage that would let one study AGN variability much more densely than in general. And the precise details of these deep drilling fields have not yet been decided in terms of the exact cadence, for example, and they're still under discussion by the Deep Drilling Interest Group. But that's a quick summary. And as I had already alluded to and had shown in the previous plot, there are other ideas of how this special 10% of the time might be used, including, as I show, the North Ecliptic Spur region, where one can do a better job studying near-Earth objects, the galactic plane region, the South Celestial Pole, and so on. People have a number of additional ideas that go beyond the main survey, and exactly how that extra 10% of the time will be spent is still under discussion. But that's my quick summary of LSST, of the main survey, and of the deep drilling fields and the other specialized cadence programs. And I'll be referring to those throughout the rest of the talk. So I'm happy to take any questions because I'm about to move on. Let me say one more word about the deep drilling fields. So if you want to learn more about the deep drilling fields, there's a number of white papers. I'm showing here just the titles of these white papers as well as the author lists. And you can see these cover topics like galaxies or blank deep fields or supernovae or mapping stellar populations in the galaxy, or deep drilling in the Magellanic Clouds, or solar system studies. And so if you have interest and want to learn more about the deep drilling fields, you can read about them in these white papers. These are all publicly available on the web. You can just Google LSST Deep Drilling Field white papers and you should be able to find them. Or if not, send me an email and I can point you in the right direction. So these are all public. So anyway, that's what I wanted to say about the cadence. That's going to be relevant to AGN studies. And I'm now going to move on to start talking about AGN selection. But if anybody has any questions before I go further, I'm happy to answer them. Is everybody good? Is everybody still on?
Yes.
Yeah.
Okay.
Yes,
Any questions, or all is good?
all is good.
Okay. Okay. Well then.
Yes. Okay.
Go ahead. Go ahead.
No, just to say that everything is okay and we are all aligned.
Great. Okay. Great. Okay. So I will continue then, and now I'm going to start telling you about the selection of active galactic nuclei with LSST. And there's a number of ways that can be combined together to select active galaxies with LSST. And these range from standard multicolor selection. And this utilizes, well, the well-established ultraviolet excess of active galaxies and quasars. This is quite effective at lower redshifts. At higher redshifts, you can use the effect of the Lyman alpha forest to give you a good estimate of the redshift and thus the source's luminosity. And these multicolor selection techniques should work pretty well based on the number of bands and based on experience with past surveys, all the way from low redshifts all the way out to redshifts of about 7.5. Beyond a redshift of 7.5, the flux from an AGN even leaves the Y-band, and so you cannot find any more with LSST data alone. Now, if you combine the LSST data with multi-wavelength data, as I'll talk about in a little bit, you can go to even higher redshift still. These techniques, especially, for example, the ultraviolet excess technique, of course, clearly is going to work the best for luminous AGNs, where the AGN's light is substantially dominating over the light of the host galaxy. For lower luminosity AGNs, of course, they will not stand out with ultraviolet excess techniques because you'll be seeing a lot of the light from the host galaxy. So those will be more challenging with that technique. So one wants to bring to bear other techniques as well. Another very powerful technique will be using variability. Again, in any given band, just for the main survey, one's going to have between about a 55 and 185 samplings per band over a 10-year period. And of course, AGNs in the optical or near infrared are known to vary substantially on such time scales. And because LSST will have excellent imaging, in many cases it should be possible to get a quite good measurement of just the nuclear flux and to see if that varies over long time scales. This should be a highly effective complement to the color selection technique, but we have not yet, in fact, calibrated in a reliable way the the effectiveness of variability selection down at lower AGN luminosities, where, again, the AGN luminosity becomes comparable to the luminosity of the host. That's something that where further work is needed, and that we're aiming to do it in coming years. But we think, at least for AGNs where one can see the nuclear light directly, for ones that aren't too heavily obscured, one should be able to select active galaxies quite effectively that way. So that's another technique. And then in addition, well, LSST will have excellent astrometric measurements, and so one can utilize those as well. One of the big contaminants in, for example, multicolor selection of active galaxies is stars. For example, at high redshifts, L dwarfs and T dwarfs are the main contaminant. And so one can hopefully utilize the lack of proper motion measured over the 10-year period to exclude many stars, because you'll see the stars moving over that time scale where the AGNs will not. And LSST is expected to reach something like 1 milliarcsecond per year at an R-band magnitude of 24, and so this should be a quite powerful technique for separating out active galaxies versus stars. It will minimize the confusion with stars. So that's one approach. And furthermore, people have ideas to use differential chromatic refraction through the atmosphere as another way of discriminating AGNs from other source classes. And so the selection of active galaxies with LSST is going to be a complex, multifaceted one, where one is going to want to fuse together standard multicolor selection with variability selection, with astrometry selection, using all of these together to get the largest and purest samples of active galaxies. And a lot of work is still needed to develop the techniques that will optimally fuse all of these different approaches together. That's something that is that is important to do in the next couple of years, and that is of great interest to the AGN science collaboration. Now, we have some estimates of how well we'll do, and I'll tell you about them in a minute. Now, in addition to just using LSST data alone, everything on this slide can be done with LSST alone. One can also utilize multi-wavelength data. And of course, very wide field surveys across the electromagnetic spectrum continue to get more and more powerful. You know, we have in the radio already some excellent wide field surveys. These are going to get only better in the near future with facilities like ASCAP and Meerkat and ultimately the SKA. Those should be very powerful complements using radioluminosity or brightness temperature or radiomorphology to select active galaxies. So those can be combined together with the LSST-based techniques to do even better. In the X-ray band, of course, we already have now thousands of observations that have been made with Chandra and XMM Newton. These will continue for hopefully the next decade, covering more and more sky. And so while these will still not cover a substantial fraction of the entire sky, one could utilize very high quality X-ray selected samples of active galaxies to calibrate the LSST-based selection techniques, where you can have very pure, reliable samples drawn from the X-ray approach, and they will be able to tell you how many AGNs are you actually finding that are out there, how many are you missing, and what is the best choice of parameters. I think X-ray data will be critical for calibrating the LSST selection effectiveness. Furthermore, eRosita, which is a German-Russian mission, will hopefully soon launch. My understanding is perhaps late in 2017 or early in 2018, and it should do an all-sky survey in the X-ray about 30 times more sensitively than the current X-ray surveys that have been done, and will discover something like 5 million active galaxies. And so that will be a very powerful calibrator as well, or the X-ray data can be used in conjunction with the LSST data to find interesting active galaxies that way. And then, of course, over on the right, I show some coming infrared missions. There are many more ground-based facilities, for example, but I'm just showing here, of course, the well-known Euclid and WFIRST facilities, which are expected to push out into the near and mid-infrared quite effectively, and utilizing the combination of infrared and optical colors. One can considerably improve the multicolor selection technique that I show there at the top and can push it to even higher redshifts, and of course get purer samples because you'll have additional multicolor constraints that can rule out stars or separate stars from active galaxies. So all these multi-wavelength techniques are going to be very important as well. Now, in this plot, then, I am sort of making some plausible assessments of what the AGN yields might be. And so what I'm showing over in the left panel is number counts of how many active galaxies have been found per square degree in the most sensitive surveys for active galaxies that have ever been done. And in my impression, and I've been heavily involved in the work, the most sensitive, most effective surveys that give you a large pure sample of active galaxies are the X-ray based techniques. So this is showing the number counts here derived in the Chandra Deep Field South and the 0.5 to 2 keV X-ray band. And what you should be focusing on here are the blue data points. And you can see we've reached a very high sky density now, okay, in the in the X-ray based surveys. At the very faintest fluxes we've ever gotten to in the X-ray surveys, you can see we're reaching a number density of about 24,000 active galaxies per square degree. So that's an incredibly high density of these things. If you scale that number up to the entire sky, you're talking about somewhat more than 1 billion active galaxies across the entire sky. So that's how many we think are out there. So if you then look at the 18,000 square degree region of the LSST prime region, prime survey area, there will be about 300 million active galaxies in that region. Actually, yeah, there'll be about 300 million active galaxies in that region that LSST should be able to detect. Now, what I mean by that is LSST will detect some flux from those systems. LSST will be going sufficiently deep when you co-add all the 10 years of data together that you'll detect some flux from them. Now, that doesn't mean you can tell that they are AGNs. You're not able to necessarily select all 300 million as active galaxies, but you will have measured flux from them. Now, actual selection of them is considerably more difficult, as I've just talked about. You have to, again, make assessments of how well you can do from multicolor, how well you can do from variability, how well you can do from astrometry, how well you can do by adding multi-wavelength, and fusing all these things together. That's what you're going to have to be able to assess. And we've only done basic assessments of that right now, and pretty confidently, being conservative, we expect to select at least 20 million, okay, of those 300 million in total, that we'll be able to say, yes, we have found this object, we're quite confident this is an active galaxy. In total, we are hopeful, if things go well, that we'll be able to do considerably better, that we might be able to select 50 million or even up to 100 million of those 300 million AGNs, but we need to do much further work to calibrate that. And that should be especially possible, reaching those larger numbers of 50 to 100 million, once one can bring to bear all the wonderful multi-wavelength data that should be gathered contemporaneously. All that together should be extremely powerful for separating out active galaxies versus normal galaxies versus stars. So you're going to need all those things together to get to those large numbers. And this is quite promising. I mean, that will be, if you can get 50 million active galaxies, that will be an order of magnitude larger than the largest active galaxy samples expected to be available at the time. For comparison, right now, we have about 1 million active galaxies that have been pretty well selected. So we're compared to what we have today, we would be increasing things by a factor of 50 to 100. This would be very important because this will give you overwhelming statistics spanning a broad range of luminosities, not just the powerful quasars, but moving down to the much more numerous, more typical, moderate luminosity active galaxies. You have these overwhelming statistics that you can investigate the evolution of active galaxies as a function of cosmic environment. How do active galaxies evolve in voids? How do they evolve in moderate density environments? How do they evolve in clusters or superclusters? With these massive samples, you'd be able to go in and really characterize that with a very high level of reliability and understand in detail how black holes have grown in different cosmic environments. So that's sort of an estimate of the yields. I also give here a reference, and I won't go through this in too much detail, but to some variability-based selection work that's been done by, I can't pronounce the name so well, Palanque de la Bruy in 2013. And again, this is giving some rough estimates of how many active galaxies you might get with variability selection, with a quite basic approach of variability selection. And if you want to see all the details of this work, I refer you to that paper, but it's just another assessment of yield. So that's sort of what I want to say about active galaxy selection, about how many we might have, and you can see we're talking about hopefully getting to 50 million or more of active galaxies from LSST. Okay, I now want to go and start telling you about some examples of active galaxy science investigations. These are described in Chapter 10 of the LSST Science book, which I show a picture of the front cover of there at the bottom. And I refer you to Chapter 10 of that science book for many more details as well as many other exciting AGN science investigations. I'm not going to try to cover them all right now. I'm just going to give you some examples. Okay, so let's first of all just give you some rough numbers. We've made estimates of how many active galaxies you might hope to find, or how many events you might hope to find, in this case every night. So every night LSST will do monitoring for about 3 million active galaxies. These will be the brighter ones that you can detect in the single epoch of LSST coverage. You'll get about 3 million that you get decent photometric monitoring for. Now, of course, every LSST doesn't cover the entire 18,000 square degrees every night. It takes 3 to 4 nights for it to do it. And so in total, every 3 to 4 nights, you'll have monitoring of like 10 million active galaxies in total. So you'll have these massive samples with excellent variability measurements that you can go out and investigate, and that will be very exciting. I'll say more about that in a minute. You should also detect lots of interesting transience events. For example, we know that many active galaxies show flares. Blazars are one example. Systems show accretion disk instabilities causing strong variability events. Every night you should have something like 50 large active galaxy flares. Furthermore, people who study stellar tidal disruption events estimate that LSST should be quite effective at finding them. And in total, you should discover, people are estimating, and this number has some significant uncertainty, but something like 3 stellar tidal disruption events every night. You'll also get interesting and exciting quasar microlensing events. You might get one of those every 10 nights. We can also hope to find binary supermassive black hole inspirals, or binary supermassive black hole even mergers. That's another exciting thing one can do. And so this stuff will be flooding in all the time. I mean, every night you'll have this coming in, night after night after night for 10 years. And so it will really become quite overwhelming, I think. After a short period of time, one will need lots of people working on the data, as well as you'll need to transition to fundamentally different analysis approaches using machine learning-based techniques, for example. You just won't be able to handle this just with physical people and eyeballs looking at data. It just won't work anymore. So that's another great challenge, is moving to the real big data regime. Now, in addition to all the AGN science, of course, we're also going to be flooded. Every night you'll discover something like 2,500 supernovae, 5 orphan gamma ray burst afterglows, many thousands of stellar flares. And so, again, it will be quite overwhelming when all this stuff is coming in. And that's, again, it's every night. Now, let's talk now just about massive AGN variability studies and what one can hope to do. So people have already done considerable work studying AGN variability, but not on this scale. LSST, again, will give you millions of well-sampled, accurate, multicolor AGN light curves densely spanning all the way from minutes out to years. This will have, you'll have billions of photometric measurements in your sample. And that's just for the main survey. Of course, for the deep drilling fields that I told you about, you'll have even better sampling by more than an order of magnitude, as well as better depth. And you'll have coverage of a smaller number. It'll be like 100,000, still an impressively large number of objects. And if the 10-year span of the LSST data is not long enough for you, of course, for the brighter objects, you can combine the LSST data with data being gathered by the Dark Energy Survey, or Hypersuprime CAN, or Pan-STARRS, or SDSS, to go out to even longer baselines. And so we should have really excellent data spanning a wide range of timescales. And with this, you can do a lot of stuff. It should be possible to powerfully study just the general luminosity and spectral variability properties of active galaxies as a function of a wide number of parameters, as a function of luminosity, redshift, wavelength, sample timescale, active galaxy color, radial properties, emission line properties, black hole masses, and Eddington ratios. Some of those, for example, black hole masses and Eddington ratios and line properties, will require at least one epoch of spectroscopy for all these sources. So getting spectra for large samples of the active galaxies found by LSST will be very important for enabling some of this science. And there's exciting stuff to be found. What I'm showing over on the right there is a plot from a nice paper by McLeod et al. where just using Sloan data, they already can see a quite clear dependence of optical variability assessed with a structure function as the y-axis as a function here of estimated Eddington ratio, such that sources accreting at a high fraction of the Eddington limit actually show less variability in the optical, which is quite interesting. And in fact, it is the opposite of what people see in the X-ray band. And so nailing down these trends and separating out this multi-dimensional parameter space of AGN variability should provide a great deal of insight into the causes of AGN variability, which are still fairly mysterious. Furthermore, it should be possible to study rare but physically important events, things like large accretion disk instabilities, or strong flares of jets in blazars, or what are called swan song events, where active galaxies which have been radiating luminously for a long period of time shut off, or quasi-periodic oscillations. These types of things will be very exciting to investigate. They'll be rarer, but the sample is so vast that you should get decent numbers of these things as well. Okay, so that's massive AGN variability studies. Also, the LSST data can be used very effectively for triggered spectroscopic follow-up. If you have a spectroscopic facility and utilize it in conjunction with LSST, it should be possible to go and do, for example, reverberation mapping. So what you would be doing here is you would be watching interesting quasars for strong variability events that are likely to trigger a reverberation of the line emitting regions. You would wait till the quasar's continuum is seen to vary by a large amount, and you would then go in and get follow-up spectroscopy to watch the emission lines change in response to the change of the quasar's continuum. This has been a very successful technique, this reverberation mapping technique, primarily for low luminosity active galaxies, and that's what I show in the upper left. Most of the active galaxies that have been investigated so far with reverberation mapping are low redshift, low luminosity objects. There are now some advances pushing out to higher redshift. You can see we are trying to reverberation map some luminous quasars, but LSST will enable such things to be done much more effectively by, again, homing in on the rare, strong variability events that are most likely to give you a good reverberation signal. Also, it should be, well, and I won't drag you through all the details, but I will also say that it should also be possible to do excellent photometric reverberation mapping. There are papers by Chalouche et al. Discussing this, where one can hope to just use the pure photometry in bands that are relatively free of emission lines and bands that cover strong emission lines, and purely from the photometry one can aim to investigate reverberation lags that way. So this will be a very powerful technique for pulling apart the structure of active galaxies, but it will require coordinated spectroscopic facilities. Here's another example of triggered follow-up. We know that many active galaxies have strong winds outflowing from them, and these winds imprint strong absorption lines in the rest frame ultraviolet, which at high redshift, of course, is redshifted down to the optical. And you can see here examples. Look at the left-hand panel to begin with. You can see examples where you see these strong absorption features here in the carbon-4 transition that are varying over time by large amounts. You can see in the little light curve shown as the inset, these things are varying by like a factor of 2 or so in strength. And so by looking for color changes in LSST bands of objects that are known to have these broad absorption features, you'll be able to home in on events where a strong broad absorption line change is occurring due to the wind structure changing, for example. And again, these events can be quite strong. As I show in the right-hand panel, you can see here's a case where a single object has been observed at a number of epochs, and the change in the ultraviolet absorption strength is really quite strong and pronounced. And this would easily show up with LSST quality photometry. So you'll be able to home in on massive samples of objects where absorption variability is occurring and catch it in the act and go and study it in great detail spectroscopically. So that should be very powerful also. Okay, and then on a couple other things related to this massive variability, one could also hope to investigate microlensing, where LSST is expected to find and monitor something like 4,000 active galaxies that are lensed into multiple images, where, as you can see in my little schematic here, you have a background quasar being lensed by a foreground galaxy, and you see the multiple images being shown there. Now, the LSST's Cadence is, in fact, well suited to the identification of microlensing events, where stars in the intervening lensing galaxy cause flux changes in one of the images. And what is happening here is the star's caustic is, in fact, moving across the emission region of the active galaxy and causing the flux to change. And this type of technique, if you get sufficiently high quality data, effectively give you micro arc-second resolution imaging, a kind of imaging, of the quasar's nuclear region. And so if you can target, if you can trigger dense, targeted, multicolor, ultraviolet X-ray monitoring, you can aim to constrain the accretion disk temperature profile. There's already been good advances on this. You can see in the upper right an example of a light curve where here two of the images, the magnitudes from two of the images A and B, for one particular system are changing above and beyond what you would expect just from the lensing. And that is thought to be due to one of these microlensing events. And by monitoring that carefully, you can, again, essentially go in with micro arc-second resolution, image the structure, innermost structure of a quasar. And if you could get a large sample of these, you could examine the structure of quasars as you change their luminosities, or as you change their Eddington ratios, or as the black hole mass changes, or you could look for evolution with redshift. So that should be another very exciting thing to do with LSST, this microlensing stuff. And then furthermore, people are now, even now, finding candidates for small separation binary supermassive black holes. So the idea here is that as a supermassive black hole binary system moves from parsec scale separations down to milliparsec scale separations, you likely need gas accretion to allow that to occur, that shrinkage from the parsec scale down to the sort of milliparsec scale. You need gas accretion. Stars become rather ineffective in that regime at actually removing angular momentum from the binary system. And people have done considerable simulations of this. I show in the right there one nice example of such a simulation. And this is showing a pair of binary black holes accreting from a disk shared by both of them, and the accretion rate is shown as a function of time from this simulation. And you can see there's significant modulation of the accretion disk over time. You may see the accretion rate onto the black holes varying on timescales of the binary period, which would be months to year timescales for relevant separations here, well suited to LSST monitoring. And so a massive LSST variability survey should be able to find or usefully constrain this uncertain frequency of black holes with separations of sort of 10 to the minus 2 parsecs. And I'll say that already some candidates for such systems have been found. I show in the lower right an example of a recently claimed system. I'm not sure everyone agrees this case is ironclad, but it certainly is intriguing. And with LSST, one will have a well-defined massive sample to investigate such types of events systematically. And there's a number of claimed systems of this type, and one would like to get much better sampling to find binary supermassive black holes in the universe. So that's one example of some specific science with LSST. I will now tell you about another. I will tell you about, in this case, transient supermassive black hole fueling. So people have long expected and have now found cases where a dormant supermassive black hole can flare up to AGN luminosities for periods of months to years via the tidal disruption and partial accretion of a star or even a planet or a gas cloud. And what's being showed in this upper panel is a simulation where stars are coming in and being tidally disrupted, and You can see you have some material in the star that becomes bound, other material that gets launched off in an unbound trajectory, and the bound material, when it accretes down onto the thing, is what causes the fueling of the black hole. These systems were originally found in the X-ray band with the Rosat Observatory, but they only had sparsely sampled light curves at the time. People have now been able to find these systems in wide-field optical UV and X-ray monitoring surveys with things like GALAX and SDSS and PTF and PAN-STARRS. And what you're seeing there on the right is an example of one system that is showing its variability. Well, it's actually a couple of events where you're seeing the variability, okay, across a variety of bands. So this is a selection of these events, and you can see they have a variety of properties across the different bands. And with LSST, again, you expect to detect several thousand of these types of events per year. Now, it will be, at least you should detect them. Now, whether you can, again, reliably select them for what they are is more challenging. You will have to enforce quite rigorous selection cuts to make sure you're not being confused by supernova events going off in galaxies or active galaxy events occurring in systems. But if you can employ those selection techniques, and people believe that they can, you should get a large sample of tidal disruption events that you can go and investigate as well. And what can you do with these? Well, you can hope to measure the tidal disruption outburst rate for different types of galaxies as a function of redshift, as a function of galaxy nuclear activity. That's one thing. You can also assess the contribution of tidal disruptions to the AGN luminosity function to determine how much of the general fueling of active galaxies is ultimately due to these tidal disruption events. I personally think the fraction is going to be pretty small, but we will see. Other people think it could be larger. Furthermore, we have found that some of these tidal disruption events show powerful jets in the radio and also up in the X-ray. You see a lot of jet-related emission. And you'd like to compare the optical tidal disruption events found with LSST with those found in wide field radio surveys to understand the diversity of these events, to understand why some of them have powerful jets, why some of them don't. You'd also like to understand why these things have a wide range of luminosity. Presumably that deals with the mass of the star that was disrupted back here, as well as the amount of material that ultimately got bound to the black hole versus what was launched away. So that's another important thing. And then finally, one can hope to find remarkable events among these tidal disruptions, cases where you have a white dwarf being disrupted by an intermediate mass black hole, or where instead of disrupting a star, you're disrupting a giant planet, or where instead of disrupting any kind of bound object, you're disrupting a gas cloud, a more diffuse gas cloud. All those things should be occurring in galaxies, and by understanding the diversity of these things, you can hopefully find and understand some of these more remarkable events that are expected. And that is my final selected technique, my final selected topic. I want to tell you about active galaxy investigations out at high redshifts. So here we're pushing out to try to investigate the first supermassive black holes in the universe. With LSST, it should be possible to select active galaxies out to quite high redshifts. These will stand out quite strongly just based upon their colors. As you see, look at this plot on the left, this shows the color diagram in Z minus Y versus I minus Z. And you can see that as you go to high redshifts, the colors are really tracking very strong as even all of the Z band flux is going away, and you're only getting flux up in the Y band. And again, the main contaminants will be things like T dwarfs and Y dwarfs and L dwarfs, and many of these can be removed by proper motion measurements. And so you'll be able to home in on the high-redshift AGNs. And you can see on the right, we give estimates of the number of AGNs that are expected. We expect to get some significant numbers of AGNs out to these very high redshifts, out to redshifts of 7.5, down to moderate luminosities. And so the yield should be large. You can see that just for above redshift 7, we expect to get a couple thousand of these things if we're able to go down to the very faint flux limits. So we should have large samples of very high redshift objects, and we will also be able to go and take sources that are detected in the X-ray band or in the radio band that we're quite confident are AGNs already, and we can use the X-ray and radio signatures combined with the LSST photometry to identify them as AGNs as well. Now, what about going to even higher redshifts? Well, LSST alone can't do it by itself because the flux drops out even of the Z-band. But if you combine LSST with wide field near-infrared data, for example, from Euclid or WFIRST, you can expect to go to even higher redshifts. And that's what's shown here. This is a little schematic showing the sensitivity limit versus wavelength for LSST and for Euclid and for WFIRST. And you can see that especially WFIRST is quite well matched to the LSST sensitivity and extends great sensitivity all the way out to like 2 microns. And so you should be able, with this technique, to actually select AGNs out to redshifts of like 10. And the sort of estimates are that Euclid should be able to discover large numbers of objects out to, and you see it's like 1360 objects at redshifts greater than 7 and 24 at redshifts greater than 10. And with WFIRST and LSST together, over a smaller area, like 2,000 square degrees, you should be able to get something like 29 quasars at redshifts greater than 10 and 1490 at redshifts greater than 7. So here you'll have these massive samples of active galaxies out at high redshifts that you can go and investigate. And here's a little schematic showing sort of luminosity versus redshift for the types of active galaxies we might expect to have out in the 2020s. What's shown here are X-ray selected active galaxies as the blue and black dots from Chandra and XMM surveys in blue, and from the expected Athena mission in black. And you can see with Athena you'll be able to get out to quite high redshifts from the X-ray based technique. But then with LSST and with the infrared surveys, you'll be able to do even better, for at least for unobscured systems. And you can see there the Euclid objects in the blue, and what WFIRST and LSST together can do at high redshifts. And here I'm just showing the data points for WFIRST and LSST at redshifts of greater than 8. If I showed the entire redshift range, the whole plot would quickly turn red, because there'd be like 50 million points in the plot. And so I'm just showing the rare high redshift objects to illustrate that LSST can fill in this critical area of moderate luminosity active galaxies out at high redshifts. Okay, we can also then, once we are able to find all these objects out at high redshifts, we want to understand their physical properties. Now, so far, even when we've pushed out to the highest redshifts, multi-wavelength studies at the highest redshifts have shown little evidence for spectral evolution. Here I show one example where I show with this alpha OX parameter the ratio of the X-ray and optical flux, which doesn't seem to change very much from low redshifts and high redshifts. Okay? But there have been some notable exceptions where now at high redshifts people are starting to find a few examples of quasars that don't appear to have any dust. They're very infrared weak, and this is from this paper by Zhang et al. That I show, and you can see a couple of very infrared weak quasars there, and one would like to, again, push these types of studies to even higher redshifts, because at some point you figure the population has to start evolving in its physical properties, and we want to look for that. Okay, and then just to end, I want to end by just telling you about the LSST science collaboration, which you might be interested in, and future plans. So the LSST AGN science collaboration currently has 38 members, and I list them there over in the right. These are primarily people in the United States, as well as Chile, and there are now some people joining from the UK who have because the UK has recently joined the LSST consortium. The AGN Science Collaboration is presently working as a loose confederation of people, but we hope if we can secure funding that it can become a more hardcore collaboration as the LSST construction proceeds. That's going to be challenging because funding is always very tight, but we hope to do that. Currently, our work has been sort of bootstrapping our way along to get ready for LSST, where we're currently working on things like the deep field surveys and Stripe 82. We will all soon start working on data from dark energy survey, and then we'll also work on data from pan-stars, and then we'll move to surveys like SUMARRAY, and step by step here, we're getting closer to the sort of data quality and data volume of what LSST will ultimately provide. And so this is going to be a step-by-step process as we build ourselves up for the full data stream that LSST will ultimately give. And there's a huge amount of work that's still needed. I've highlighted some of it in terms of just AGN selection needs a huge amount of work still, as well as simulating LSST effects on variability, doing detailed science planning, planning out how one might best pool all the observational resources together. And if you have any feedback, I give the email address there. I also want to highlight that we have a web page for the LSST AGN Science Collaboration. Here I'm just showing the web page. You can see the web address there in the upper left. And you're welcome to go there and check things out. It's not fully fleshed out, the web page, but we do have information right now. We have a tab for meetings that are coming up. We have a number of slide sets that are posted there. We have a membership list. We have also the procedure by which people who are members of the LSST consortium are able to apply to join the AGN Science Collaboration, and we have general contact information. So by all means, go and check that out if you want some further information. And I also want to highlight that we have a team meeting coming up. It's going to be held as part of the 229th AAS meeting, which is being held in Texas on January 3rd is when the LSST Science Collaboration Roadmap meeting is occurring. I give some details of it here in terms of where it is and when it is and so on. I list the organizers. I'm one of the organizers. Ohad Shemer and Gordon Richards are two of the other organizers, and you might be interested in attending this meeting, where if you're going to be going to the AAS for other reasons, people are welcome to attend this meeting. Even if you're not a member currently of the AGN Science Collaboration, all are welcome at this meeting, and you can get in contact with us if you're interested in attending. And I will end with that, and thank you very much, and I'm happy to take any questions.
Okay.
Thanks.
Clever class. Thanks, Neil.
Yeah, sure. I'm happy to take any questions. I'm not sure how it will work. I'll let you kind of guide how this should go.
Okay, I have a question. Here's Luis. Hi, Neil. Thank you very much for your presentation.
This is Luis da Costa?
Yeah, that's right.
Okay.
A couple of questions.
Sure.
How often you meet, the collaboration?
In person?
Well, no, even remotely.
Remotely? Occasionally. Most of the discussions are currently happening by email. Mm-hmm. The challenge, I mean, and there have been some phone cons, but they're fairly rare. And this meeting we're hoping will kick off a lot more of the sort of road mapping activities. Here's one of the challenges right now, and I'll just speak very bluntly. In the U.S., there's very little funding right now to actually plan for science with LSST, and this is a great challenge. It makes it so that many people, just are not able or not willing to invest a lot of time in it. So I would say that there is a selected subset of people right now that are most energized and are doing sort of most of the work that's actually occurring. Hopefully, we hope to engage many more people, but again, I think that will take a change in funding and so on. So that's the situation there.
Actually, that leads to my second question. What is the role of the LSST Corporation on that? If I understand, it was to sort of sponsor exactly that, right? Exactly.
So the LSST Corporation is trying to help with this. Okay, they have a lot on their plate, the LSST Corporation, but they are trying to be helpful in this regard. And so one thing they are doing is they are funding meetings like this one that I'm showing as this slide. The reason why it's possible to have this meeting is because we got financial support from the LSST Corporation. They are funding support for, renting the room, they're funding some of the travel, and so on. And so that's extremely helpful. And so that's one thing they can do. Now, that's not still the kind of support one needs to actually accomplish the massive amount of work that is required. So the LSST Corporation is planning to actually approach, in fact, private donors in the United States to see if some of them, private foundations in the United States, to see if some of them would want to get engaged in supporting this kind of road mapping work or this kind of real science planning work that really needs to be done. We are hoping that that they will be successful in that, but that is not yet decided. In fact, there's a deadline fairly soon for people in the U.S. to submit proposals for such funding, and so that's something that is ongoing. So again, the LSST Corporation is a good thing. It definitely is trying to help. They have a lot on their plate, and in the U.S., just the funding situation, for example, at our National Science Foundation is so tight that usually they are only funding projects where people already have data and are ready to go with the data. They're not as excited about funding something that's going to happen in 5 years or 10 years, just because they're overwhelmed just with the people who have data right now.
Let me ask you a final question. One thing that always puts me uncertain. how will you guys imagine bringing together, the knowledge and preserving it to be able to actually analyze this as a level 3 data set? You're going to have your own machines. You're going to try to use LSST data access centers. How do you imagine this evolving in time?
Well, I think a lot of it's going to have to be done on the LSST data access centers. I think that makes a lot more sense in terms of, certainly whenever you're going to the pixel data, I think that's going to have to be that way. Clearly, with catalog-based data, one can do quite a bit just based on the the processing. So let me say, another thing that the AGN Science Collaboration has been doing is we are frequently answering questions from and providing input into the main LSST cataloging enterprise, trying to ensure that the catalogs that are made will be as useful as possible for active galaxy studies. For example, ensuring that once we have samples of strong AGN candidates, they go in and do the best possible nuclear photometry, the photometry of the nuclear point source, getting out as much of the extended starlight as possible. So there are a number of things like that that we are doing. So we are trying to guide the main cataloging effort so that it will be useful for the AGN stuff. So anyway, that's that. Now, in terms of how do we envision managing this huge amount of data, how do we envision accomplishing all these things? Well, yeah, this is a major problem, and a number of us have been saying this is a major problem for years now, because this is not something that you give out. You give a couple people, $20,000 or $100,000 and say, go do it. That's not what this is going to take. If you really want to do this well, it's going to take millions of dollars. But nobody has millions of dollars to do it. And so hopefully the science agencies in the U.S., as LSST gets closer and closer to coming into operations, will realize this and will really start supporting this stuff. Again, as I say in this slide, we want, right now we're sort of working as a loose confederation of people. We want to become a hardcore collaboration. We want to do that. We want to operate the wafers work. Those people are used to dealing with massive data sets like this and have built up the overall approaches to do it. But, it just isn't, but of course they have a fundamentally different way of doing things. They have a fundamentally different funding model where they actually fund a collaboration to execute a specific project. Many of the science agencies are just not in that mode right now, and we are hoping they will get more into that mode as things get closer and closer. I mean, it may take almost a crisis before they will change. Suddenly a crisis will occur, LSST will be about to start, no one will be ready, and suddenly the money will start flowing. That's usually the way things work in the U.S. It takes a crisis before you get real change.
Yeah, it's actually very different from, for instance, Euclid, right? That people actually is a very structured organization. Yes. All
That's
codes
right.
have to be approved. I mean, do you envision people sharing their codes? I mean, open source kind of policy?
Yeah, I would like it to be that way. Again, the problem, the situation right now is that it's a loose confederation. As you're correct, that Euclid has a fundamentally different structure. And there, that's because NASA has a different way of doing things. But here, I mean, the problem is, yes, we would like it to be that way. That's what we envision. But right now, there's no way to really enforce that. And most of the people were happy to get them to do very much at all. And so the few of us who are doing things, do what we can to energize everybody. But that's what's happened. That's the situation so far.
I also think, looking at your list of members, I also think that there is also a competition from other projects, right? I mean, I see an enormous lack of names from people involved in Sloan 4, EBOS.
Yeah, absolutely.
Greatly, right. I'm sure they want to join also here, but they're just too busy right now.
That's exactly right. These people already have data right now they're working on. They have funding for the data they have in their hands, and when you have a funded project right now and an unfunded project 5 years in the future, the choice is pretty clear which one you will put your effort into. Now, again, so right now, that's what I say here about this basic bootstrapping approach. The only way I can see this working, at least given the way the funding model is right now, is to go with a step-by-step approach. To start right now with the data we have in our hands, things like deep fields and Stripe 82, then to move to things like dark energy survey and pan-stars, then to move to things like SUMARRAY, because then each step you will have data, and you can propose exciting science projects step by step to do this, and you'll be getting ready little by little for LSST. Absolutely. I just don't think there's any support right now for to say something like, well, there's all these great LSST simulations that are out there, and there really are from the data from the LSST data teams, and I want to spend a whole bunch of time sitting around analyzing these simulations to figure out how to discover AGNs. No one is interested in doing this because they have real data right now, and they're focusing on that.
All right, thank you very much, Brent.
Yep.
Appreciate it.
Okay. Hopefully, I mean, because I can't see you, I'm not able to tell the sort of feedback, but hopefully that is helpful answers.
Yes, they were.
Okay.
And here I just decided to show myself. I mean, we try to preserve the bandwidth. That's why we don't put our camera on.
That's fine.
Appreciate it. Thank you very much.
Okay. Are there any other questions, or is that all?
I think that's all.
That's it.
I have no questions.
Okay.
Very good. Thank you very much.
Very good. Well,
thank you very much.
Very, very good. It's been a pleasure speaking with all of you. I hope this was helpful, and good luck as you plan your LSST efforts.
Thank you.
Okay. Take care.
Bye-bye.
Bye. Bye.